We're going to take a look at another math notes video here. This is going to be mathematical induction for series. This is section 10.1.5. And we'll go through this. We'll go through an example because this can be kind of a tricky topic. I'll try to make it as straightforward as possible. So to start off, most of the proofs you've written so far have been about geometric situations. But proof is important in all areas of mathematics. While many theorems in algebra are proved by methods similar to those used for geometric proofs, but proving the formula for the sum of a series for an infinite set of values requires a strategy called proof by mathematical induction. Mathematical induction can be used to prove that an expression represents the sum of a series is true for all integer values of n greater than a specified value, typically greater than or equal to n equal 1. To prove the sum of a series using mathematical induction, follow the steps below. Step 1. Verify by substitution that the relationship is true for a specific value of n, typically n equals 1. So check to make sure that your expression works for a specific value. Assume and state that the relationship is true for n equals k. So we're going to plug in a k term and rewrite the equation. Extend the relationship to the next integer, k plus 1, by adding the k plus 1 term to the original sum. Algebraically prove that this relationship is true for n equal to k plus 1. Write a concluding statement of what has been proven. The statement usually begins with, therefore by mathematical induction, ... Alright, I'm going to have an example here of a series on the next slide. So we have a simple arithmetic series here, 7, 9, 11, 13. We can figure out the equation for this series. We have a common difference here of 2. We're adding 2 to each term. So that's going to be our slope. If we went back to our 0th term, that would be 5. So our equation here for t of n is 2n plus 5. And that's written here at the end of the series after the ... dots. Okay? Now we need to find the equation for s of n. And I have it written out, but let's go through the process of finding that as well. So for the sum up to the nth term, we're going to take our first term, which in this case is 7, plus our last term, which in this case is 2n plus 5. And we're going to do 1/2 times n. So this is going to be 2n plus 12 times 1/2 n. If we distribute the 1/2 n to both of these terms, we're going to get n squared plus 6n, which is what we have right here. So if they give you the problem written out, 7 plus 9 plus 11 plus 13 ... plus 2n plus 5 equals n squared plus 6n. This last term is your t of n equation, and what it's equal to is the s of n, or the sum equation. So I'm going to erase the work here. So on the last slide, what we were saying by proof of induction was first test to make sure this s of n works. So let's do that real fast. They said you could test it on the first term or the second term. I like to test it on the second term. So I'm going to test s of 2. And I know that s of 2 would be summing these two terms, the first one and the second one. So s of 2 should equal 16 because 7 plus 9 is 16. Let's see if it does. So we take 2 squared plus 6 times 2. We're using our n squared plus 6n equation, which is our s of n equation, and just substituting in a 2 wherever there was an n. So that gives us 4 plus 12, and sure enough, 4 plus 12 equals 16, which we can see we get when we add 7 plus 9. So we've checked to make sure that it works with a numeric value. So let's go on to the proof by induction now. So once again, I'm going to erase this. So proof by induction says, okay, we know that it works for a specific value. We just tested it on 2. But does it work for all the values? To test that, what we're going to do is we're going to make a little assumption here. We're going to say that if we were to sum up to, say, the second term, and we were to add the third term, that would equal the sum up to the third term. So that makes sense. In this case, we already showed that the summing up to the second term was 16. If we added the third term, so the sum to the second term was 16, adding the third term of 11 should give us 27, and that should be equal to the sum up to the third term. Again, we can test that numerically by plugging in S of 3. So that's 9 plus 18. 9 plus 18 equals 27. So that checks out. So this was an example of a proof by induction using known integer values. We took the sum up to a certain number, we added the next number, and that equaled the sum up to that next number. So we're going to take the same idea and write it out in variable form. In this case, we're going to take the sum up to any term, which we're going to call k. We're going to add the next term, k plus 1, and it's going to equal the sum up to k plus 1. So just like in this case, in our little example here, k would be 2. 2 plus 1 is 3, and that would equal to the third term. Let's test this algebraically now. So S of k, I'm going to go to my S of n equation. I'm going to plug in k for n. So wherever there was an n, I'm going to plug in a k. So this becomes k squared plus 6k. T of k plus 1, I go to my T of n equation, and I put in k plus 1 wherever there was an n. So instead of it being 2n plus 5, it's going to be 2 times k plus 1 plus 5. Don't forget your parentheses, those are important. And we want to show that this equals S of k plus 1. So we go back up to our S term, our S expression, and we write k plus 1 squared plus 6 times k plus 1. So this is the k plus 1 gets replaced for the n here and for the n here. Now we just do some algebra and show that these two things are equal. So I'm going to do k squared plus 6k. Going to distribute this 2. That becomes plus 2k plus 2 plus 5. I'm just going to work the left-hand side here. We have like terms there with the 6k and the 2k, and like terms with the 2 and the 5. So we're going to combine those like terms. 2k plus 6k is 8k. 2 plus 5 is 7. Over on this side, k plus 1 squared. So I need to go back and remember this. A plus b squared is equal to a squared plus 2ab plus b squared. Students often forget this middle term. So we say we square the first term, we multiply these two together and double them, and square the last term. That's the shortcut method rather than writing out the area model. So if I square the first term, that becomes k squared. 1 times k is 1k, and I double it, so it becomes 2k. And plus 1 squared, which is just 1. Distribute the 6, so that's plus 6k plus 1. Now I have some more like terms on the right. 2k and 6k are going to become 8k. Oops, so 6 times 1 here, this should be a 6. Then 1 plus 6 becomes 7. So this on the right side becomes k squared plus 8k plus 7. the left equals the right. So this checks out. So what we've just shown is that this will work for any value of n or k in this case, any integer value, this will work. We showed over here that it works for specific integer values of 2 in this case, but now we know because we use variables that it'll work for any integer value. So therefore, by induction, n squared plus 6n is the sum of this series for any value of n greater than 1. All right, guys. Thanks for watching. Have a good one.